started on the group theory as such, and we're going to meet the definition. Now, the way he structured this chapter is to look at some examples beforehand. It's quite often people do this in mathematics before they rather than diving into the definition straight away, people often like to give some important motivating examples to begin with. But I'm just going to dive straight in and look straight away at the definition of a group. Okay. Then I'll come back to these some of these motivating examples he has in the beginning. Okay. Because I think we've been dancing around it for too long, so we may as well meet the definition. So what is a group? So a group is in the setting of where you have some set of objects or elements. In various examples, these might be sets of certain types of numbers, or there might be a set of certain types of functions, or a set of certain kind of matrices, or lots of other situations as well. So you've got a set of elements, and you've got what's known as a binary operation, which is represented here as circle. So you should think of this circle symbol as, like one example of a type of binary operation you could have is just addition of numbers or multiplication of numbers, and it's the same symbol we use, composition of functions. Okay, so any binary operation like this, which is a way, so the binary there refers to that there's two inputs into the operation. So you take two elements from the set, and this operation, just represented abstractly here as a circle, gives you a new element, a circle B. Just as if I give you two numbers, you can form a new number, the first one plus the second. Or you can use multiplication, the first one multiplied by the second. Or if I give you two functions from a certain space to another space, provided they line up right, you can compose the two functions. So you give them two functions, you can perform one function after the other, and that compound function, that composition function, is a new function. You get a new example of the object. So this is the setting for a group, the set with the binary operation on it. Now the universe of examples of that kind of thing, a set with an operation on it, is vast, huge. We want to restrict it a little bit. We want to only study situations where we see a certain type of pattern occur. If you like, a certain level of nice behavior of the operation on the set. Okay, not to be too restrictive, because if we insist that our function behaves too nicely, we'll be restricting that universe of examples down quite a lot, and what we're talking about won't be as general or won't be as applicable as it could be. But at the same time, we are only interested in objects that have some mathematical meaning to them or some nice mathematical structure to them. So we don't just want to be considering arbitrary sets and arbitrary operations. So the four properties that we ask for, they're commonly referred, we can refer to them as the four parts of the definition of a group, or they're sometimes referred to as the four group axioms. Because if you like, these four statements we're about to talk through here, the first one is kind of hidden in the preamble there. They're sometimes referred to as the four axioms. You can take them as the foundations on which all of group theory is built. So all the theorems and results of group theory, in some sense, are a consequence of the four conditions in the definition. So it's not declared here as such, but it's implied in the introductory paragraph, is the first axiom is a closure axiom. So here you see the binary operation set up that it's a set, it's a function, circle, from the set of ordered pairs to the set G. So in particular, I'll just put this note on the overhead. In particular, what that means is so in other books, you will see the first group axiom. First group axiom is the closure. And that says for every pair of elements, so for all G1 and G2 in the group. Now this is implied by what he has in his preamble there to the other conditions. So for every pair of elements in the group, this new element that you get is still in the same set. Okay, so this is the sense of being closed. Set is a closed system with regard to the operation of whatever the operation is. Okay, so taking elements and combining them using this binary operation, it never takes you outside of the set. That's one of the things we insist on. So when we look at a particular group, the set G, it's a closed system. We're never applying the operation is never going to take us out of that. Now, this is implied in Judson's, implied by Judson when he says that the binary operation, when he says that the binary operation is a function, circle sending the Cartesian product of the group with itself. Remember, that's the set of all ordered pairs. So that's going to be the set of all possible G1s followed by a G2 that you can form. When he says that this is a function to the set G. So the value taken by this function, when you apply it to the two arguments, again, the codomain for that brings you into G. Okay? So setting the situation up like this, as he does, that implies this sense of G. Okay? In other books, or when it's presented by other people, they sometimes say, so a group is a situation where you have a set with an operation defined on it. And they leave open the question of where the product elements live. Maybe they could take you outside the set, maybe they could keep you within the set. And then they introduce the closure axiom as the first condition that we require to be called a group. Now do stop me at any point if you'd like clarification on something or anything. Okay. So we can take that idea of closure being the first condition. Then we have these next three properties: associativity, existence of an identity element, and an inverse element. Now these, I'm hoping these concepts should be familiar to you, somewhat. The first is that we insist that the operation is associative. So that if you want to form a product of three elements, an A, B, C, you see, I can't just write down A circle B circle C, because that's slightly ambiguous. It could mean this quantity here, which is first A circle B, then with the result of that circle with C, or it could mean, well, first circle B with C, and then with the result of that, form the product A circle the result of that. Associativity is when these two ways of evaluating that product of three elements always gives you the same answer for every A, B, and C in the group G. Okay? Certainly addition of numbers acts like that. Certainly multiplication of numbers acts like that. Doesn't matter in what way you evaluate the addition and the multiplication. Multiplication of matrices acts like that. Composition of functions acts like that. So it's a very common pattern to see in meaningful mathematical operations. Next condition is the existence of a special element called the identity. Property that this special element is asked to have is that when you take the product of it with any other element A, on either side, it just gives you back the same element A. Okay? So it doesn't change the other element. Then we have the inverse element condition. So having talked about the existence of a special identity element, the inverse condition says for every element A in the group, there must exist an associated element, which we refer to as A superscript minus 1. We read that in English as saying A inverse. Such that when you form the product A circle A inverse, either way, you always get the element A. Now you should recognize that kind of pattern. Like talking about certain kinds of matrix have an inverse matrix. Multiply them together, you get this special kind of matrix, which is called the identity. So similar language being used. And indeed, those examples from the settings of matrices and so on, they are indeed examples of groups. What's left a little bit vague is, for instance, it says there exists an element. It's a little bit vague on whether there's one and only one element like this. So it's not specifying that there's one and only one element. Maybe there could be a few identity elements floating around. That's something which will settle very soon. And similarly with the inverse elements, for a given element A, maybe there could be more than one inverse element floating around. So that's not explicitly stated here, but we'll soon see that that issue is determined. It is a consequence of the group axiom, so there has to be one and only one inverse and one and only one identity. Also, this condition here, it's left open the possibility that A is its own inverse. Okay? When you first read this, it seems to be talking about a different element, A inverse to the original A. But no, it could be that an element acts as its own inverse, so that when you take the product of A with itself, you can get back the identity in some particular case. So that's the definition. That sets up this general pattern of behavior of a set together with an operation. And if the set and the operation look like this, we refer to it as one. We still haven't formally met any groups at all. We still haven't formally met an example of it. Just because you write down a definition of a kind of an object and properties that you want to be true doesn't automatically mean that such things exist and that it's meaningful to talk about. But we'll soon meet several different examples of groups, several different situations in mathematics that you're already aware of somewhat, where we do have. Another thing to say about it is that it's very important that the group consists of two things: the set of objects and the particular operation in the set. Okay? Because there will be situations where we can have the same set, same underlying set G, which might form a few different groups, depending if you use a few different types of operation. Okay? So, strictly speaking, the group is a pair of things, the set and the operation. Now, we'll sometimes, when we get comfortable with it and when it's understood very clearly from the context, we won't always be explicitly mentioning, the group G, comma, whatever the operation. Sometimes we'll just fall into a way of talking about the group and we'll just name the underlying set, and it will be clear from the context and there should be a clear understanding of what the particular operation at play is. But if there's any ambiguity or if there is any uncertainty about what the operation is, either if we're producing work, we should specify clearly what the operation is. Okay, so let's look back at so what we'd like to do now is reel through a load of examples, just to emphasize that this is a meaningful definition to give, and also start to see some of the examples of groups that we're going to learn a lot more about in the course. First of all, probably the easiest one to appreciate, and perhaps the one that pops into mind the most, is the basic system of numbers of the integer numbers and the operation of addition. Okay, so this is the underlying set. So the integer z takes the role of g here. And the circle operation we're talking about is just a familiar addition of integers. Okay. So when we go through the four properties, we should quickly see or quickly understand that those four properties for a group are satisfied by this example. When you take two integers and you add them, do you always get another integer? Well, yeah, you don't get any other kind of number. When you add two whole integer numbers, you again get an integer number. So it's certainly closed under the operation of addition. Is it associative? Well, yeah, our understanding of addition is that addition of numbers is associative. So if I write down the sum of three numbers, it's unambiguous what the value of that is. To evaluate it, you have to evaluate it in a pairwise fashion to build up to the sum of the three numbers. But whatever way you do that, you will always get it. And then we have the existence conditions, the existence of an identity element and the existence of an inverse. So it should be clear that the identity element is 0. Because the property that the identity element is supposed to have is that, I keep losing my mouse keeps wandering onto the laptop. The property this special identity element has to have is that when you combine it with any other element using the operation, you get back the other element. So the question then is, well, what's this special integer that when you add it to any integer at all, it always gives you back whatever the other? Well, that's clearly the integer 0. When you add 0 to some number, it doesn't change the number. And then what are the inverse elements? Well, so given, for example, given the integer 5, what's the other special integer such that when you add it to 5, you get back the identity element, which we now know to be 0. So what you add to 5 to get 0, well, clearly you add minus 5. And that's true in general. So the inverse elements that we're talking about are the negatives. And the inverse of minus 4, for instance, minus 4 is a perfectly good integer. That's the inverse of it, well, it's plus 4. Okay, so when you add minus 4 to plus 4, on either side, you get back the identity element 0. Okay. The next example there that it's going to talk through is the example of the integers modulo n. Now those, we investigated these quite thoroughly in the number theory last year, and we even used the terminology of groups somewhat throughout the unit. So I'll leave you to talk through that yourself. And then, of course, a negative type of example. There's another obvious candidate operation that might hold to, which is the operation of multiplication of integers. Now, that's a negative example. That does not form a group. But you only realize that it doesn't form a group at the end of checking the axioms, because the first 3 axioms do check out. The integers are closed under multiplication. You multiply 2 integers, you're going to get another integer. Multiplication is associative. Is there an identity element for multiplication in the integers? Yeah, just 1. You multiply an integer by 1, it leaves the other integer unchanged. What are their inverses? Because there's no proper fractions in the integer. So what's the inverse of the integer 2 with respect to multiplication? So what do you multiply by 2 in order to get back 1? So you want to say a half. The problem is, although the half is floating around in the universe of mathematical objects, it's not in this set. And that's an important element. Here, see the fourth axiom, there exists an inverse element in G. Not just somewhere out there in the ether, but actually in the system we're talking about. Okay? So all these features have to be present in the underlying set. Okay, so integers under addition, yes. Integers under multiplication, no. In some of the other examples and in the exercises, it takes you through some of the other familiar numerical examples, like the real numbers, rational numbers, and so on. So there's a few other positive and negative examples that you can construct with the other number systems. So let's look at another type of example, a kind of an example that isn't based on a number system. And it's this example here. Now, this is our first look at what's called a symmetry group. And we'll be examining, we'll see these throughout the course. They're an important example of a type of group that there are, and they provide many of the interesting examples. They display many of the interesting group theoretic properties and features that we talk about. And they're definitely non-numerical, so it gets us away completely from that safe, familiar thing of talking about integers or real numbers. So the objects here that we're talking about are transformations of the plane. The type of things that are up for consideration as elements are what are called isometries, or distance-preserving transformations of the plane. Now, what that means in practice is we're going to be talking about transformations of the plane of the type of, well, okay, so translating the plane qualifies as that. But that won't occur as symmetries of an object, because when you translate an object, it moves it somewhere else entirely. So the kind of things we'll be talking about are rotations and reflections. So rotating the plane about some fixed point. So to rotate the plane, you fix some point, which is the center of rotation, and then the whole plane, like the fabric of the screen, I can pick it up, I can spin it around this fixed point of my finger by some particular angle. So to specify a rotation, you want to specify the center of rotation and the angle. And then reflections. To reflect the plane, we're going to reflect it in an axis. So we need a line, which is going to be the axis of reflection, and then the points on opposite sides of the line get sent to each other across them. So a symmetry of so this is a non-square rectangle. What we're asking for is which of those transformations of the plane leave the rectangle, so disregard the vertex labels for the moment, just the pure rectangle, leave the rectangle as a whole unchanged. Still the same rectangle sitting on the page in front of you. Well, when you start to think about the possibilities, you realize that there are exactly 4. Okay? You can certainly pick the rectangle up and rotate it 180 degrees. Rotate it 1/2 turn about its center. That's certainly a symmetry of the rectangle. You can reflect it in a vertical axis. So the rectangle has this vertical axis of symmetry. Okay? Then you can flip it about that central vertical line. It's still the same rectangle. You can also flip it about its horizontal axis of symmetry. It's still the same rectangle. And the fourth one, which you maybe don't think of straight away, is the trivial transformation, just the identity transformation of the plane. Just taking the plane, just sending every point to itself, not changing anything. So those are the 4 elements that we're talking about. And so this is a group of order 4. It's got 4 things in it. And the operation is the most natural operation that we think of with functions, especially functions from a space to itself, and that's the operation of composition. Okay, so composing. Now, with the aid of these vertex labels there are put there so you can help visualize the action of the thing. So the identity doesn't change everything. The 4 labels are still in the same place. It's 180-degree rotation. So you think where the labels go, we rotate 180 degrees. The A ends up over here. D ends up there. And similarly, so you can just visualize easily the action of reflecting in the vertical axis and reflecting in the horizontal axis. Now, we'll also, so the claim is that this forms a group. So let's assess that claim, confirm it, hopefully, and we'll also have a look at what's called the Cayley table of the group. So this is just a little bit more on the group of symmetries. Group of symmetries of a rectangle. It's traditional in mathematics to use the symbol gamma. So this is the capital Greek letter gamma. It's traditional to use that to denote a symmetry group. I'm simply just going to draw a little representative rectangle in there. So this is gamma of the rectangle, the group of symmetries of the rectangle. So as a set, this has 4 objects in it. E, R, H, and V. And those are meant to be descriptive labels, so you can guess what they are. E is the identity transformation. R is rotation by pi radians, like the center. I don't know what to say whether it's anti-clockwise or clockwise. It's half turn, so it has the same effect whether you go anti-clockwise or clockwise. H is reflection in the horizontal axis. And V, reflection in the vertical axis. Okay, so those are the 4 elements that are in my group, and the group operation is composition of symmetries. Okay, just the regular taking, because these are all symmetry, these are all functions from R2 to itself, from the plane to itself, so we can compose them with one. So let's assess the four conditions. Now, maybe we might need proof type arguments here, or maybe we just want to confirm that, yeah, these, in this case, the group axioms just corresponds to things we already know. So, first thing is closure. If you compose two of these symmetries with one another, is the overall composition of functions still a symmetry? Yeah, like that kind of comes just from the concept of a symmetry to begin with. Because we defined a symmetry as a transformation that left the rectangle unchanged as just a simple geometric figure, still the same four-sided figure. So if you do one of them, that leaves it unchanged. If you do another one, it's going to leave it unchanged. So the composition, nothing's changed. It's still the same rectangle. So inherently, composition of symmetries is a symmetry. That's just it's part and parcel of the definition of what a symmetry is. Transformation that leaves the thing unchanged. Associativity. The associative thing. Now, this isn't an example where we have to dive in and investigate, aspects of these particular four functions and composition and assess whether it's associative. It's a general universal fact that composition of functions is always associative. Okay? So yes, this is associative because it's a universal fact that composition of functions, when it's defined, so when you can compose the functions, it's always associative. Because if I take three functions, e.g., so let's take an x1, compose it with an x2 after an x3. So if these are three types of functions, well, when you investigate functions, really what you're investigating is the kind of values that they have. So when I apply this as a function to a particular argument, by the definition of composition of functions, this would be x1 of the composition of x2 with x3 applied to y. There's probably one more set of brackets than I needed there. So it's x1 applied to the results that you get from applying the composition of x2 and x3 onto y. When you unravel that again, that just turns into x1 of x2 of x3 of y. And if you start with the brackets the other way around, the brackets around the x1 and the x2, first for the composition, break down it in a couple of steps using the definition of composition, you arrive at exactly the same expression. Because the operation of composition just says apply the function, one function after another. So if you've got three functions to compose like that, you're just applying the one on the right first, the other one on the second, and the one on the left last. So do remember, of course, function composition is always read from the right. And that's the most standard way to present it. Then you've got identity element. Well, yeah, there is an identity element. It's already called the identity in what we've done. Okay, the identity transformation, the action of doing nothing. If you do nothing after you've done something else, the overall effect is still the something else. Okay? Or if you do nothing before you do something else, the overall effect is still just whatever the effect of the something else is. Okay? So doing nothing, either before or after some other action, does not change the overall effect. Test it out in your daily lives. It's a universal fact. It's not something special about mathematics. It's just a fact about combining operations. inverses. Okay, inverses is less, does have to be checked a little bit. Well, the identity transformation always has an inverse around, and that it is itself. So when you compose the identity element with itself, it's still the identity. Does R have an inverse? Now, it must be, if it's going to be a group, it must be one of these four. So which of those four is the inverse of R? R itself. Yeah, so it is its own inverse. Which of these four is the inverse of reflecting the rectangle in the horizontal axis? H again. Self-inverse again. If you reflect some situation in an axis, the way to return everything else to its beginning location is to reflect it again on that axis. And similarly with B. So that's kind of nice. All four of the elements are their own inverses. This doesn't mean there's suddenly 8 elements in the thing. There's still only 4 elements in the thing. Each element also plays the role of its own inverse. So it is a group. Okay. So this is a group. Okay, so it's our first example of a group which isn't just based on some familiar numbers, the integers or the modular arithmetic. So it's very different. The underlying objects are not numbers. You can't form a fraction with these, or you can't well, without putting an additive structure on the elements of R2. Just on the face of it, it doesn't really make sense to add 2 functions when you haven't specified what the underlying addition operation on the arguments of the functions are. So at the moment, we just have points in the plane, and we're performing some geometric transformation. Now we don't necessarily see all of the features of the group there. We check the axioms, we've seen what the inverse elements are. But to really get a picture of it, we would like to look at the multiplication table for the group. Except the general term for one of these multiplication tables is the Cayley table, right? Okay, that's named after a mathematician, Cayley. So look at the Cayley table for this group. Now, one of these multiplication tables, you just put the elements down in the same order, or they don't even have to go down the same order, but it'd be reverse not to. So you list them in some sensible order. We normally put the identity first. And then what we're going to display in the table is the result of all the operations in the group. Sometimes it's helpful, we can indicate what the operation is up here. So here I'm using circle in the sense of composition of functions. And what we want to see in the entries of the table is the various products. And we do have to be careful, because which project exactly do we mean? If I have a row index x here and a column index y, do I mean x circle y or y circle x in the intersection? Well, the convention is that you've got a row index x, column index y. The element we're talking about is x circle y. Okay, so it's the row index symbol on the left, the column index symbol on the right. Now, when you're drawing these Cayley tables, without thinking, you can put down the row and column corresponding to the identity element. Remember, the identity element doesn't change the other elements when we perform the composition. We've also already recorded what all the inverses are. Each element is its own inverse, so that will allow us to fill out the diagonal. Each element composed with itself, because each element is its own inverse. You compose an element with its inverse, you get the identity element. Okay. So now there are a few products which are undetermined as yet. What is R composed with the horizontal reflection? What is R composed of the vertical reflection? What are those products the other way around? Horizontal reflection composed with rotation, and vertical reflection composed with rotation. Well, strictly speaking, to figure those out, we probably have to return back to our diagram of the rectangle. So here's the starting off rectangle, A, B, C, D, just label as vertices. Now we want to examine one of these products. So let's first rotate it. When you rotate it, that flips, so the A comes over here, the B is going to come over here, C is going to get rotated over there, and the D is going to go over there. Then let's perform reflection in the horizontal axis. But we're performing it on this middle rectangle, yeah, which is the result after we rotate it. So if we then reflect this in the horizontal axis, B goes up here, C comes down here, A goes up there, and D goes up there. So that's the composition R after H. That's what we have, sorry, H after R. Yeah, be careful to get your compositions the right way around. H after R. But this must be one of those first four symmetries. So which one is it? Now we're obscuring the middle picture, just looking at from start to finish what has been done to the rectangle. Well, we know it's been rotated and reflected in the horizontal axis, but in one go, you see it's been rotated in the vertical. The A and B is swap positions, and the C and D is swap positions. So that tells us that H after R is V. Okay? And by doing a similar investigation, drawing the rectangles, you'll come up later on with more efficient ways of doing this, and we'll learn more about symmetries of regular 2D shapes. We'll learn enough about them to very, very quickly be able to handle all the products. But for the moment, we might have to investigate each one by drawing those rectangles. But it's fun and it's good to do. It gets you to deal directly with them. So H after R is V. So at least that's one entry in the table here. H, so it's good. So it's the thing on the left, circle the thing on the right. So it's this entry down here, H after R. It's going to be V. The other ones will be R after H will be V, R after V will be H, H after V will be R, V after R will be H, and V after H will be R again. So that's how the table completes. Now to justify all those ones that I just threw down there, from first principles, you probably have to return to these kind of pictures to justify each one of those. I'm forgetting to record the screen. Sorry about that. But you'll have the scans of the pages and the audio. So you have to remind me in the future to record the screen. Okay. And kind of then on that page then, because there's only 4 elements on it, in that page is more or less, can be found on that page, kind of everything there is to know about this system as a group. Okay, and what more could we say about the operation of composition in these 4 elements? Okay, we haven't missed anything out. We've seen the identity element, we've seen what the inverses are, we've seen all 16 of the various products laid out. Good. Now there's another example done there. Let me just quickly switch back to computer. So in a very similar way to looking at the symmetries of a rectangle, they then go on to look at the symmetries of a triangle, a regular triangle, an isosceles triangle. Turns out you've got 6 of these. Again, the identities, but now you have 2 non-identity rotations, because you can rotate the triangle by 1/3 of a turn. So this is, you've gone clockwise, unfortunately. I preferred it if you'd gone anti-clockwise, but no matter. So this rectangle here has been rotated 1/3 of a turn clockwise. That's how it moves the vertex. This is rotation by 2/3 of a turn clockwise. course, whether he's gone anti-clockwise or clockwise is a bit ambiguous because he's not stating the angles here. So that's just me saying that this one is a third of a turn. But maybe it's 2/3 of a turn anti-clockwise, and this is 1/3 of a turn anti-clockwise. It's a little bit ambiguous. So there's 2 non-identity rotations that you can do to the triangle, and then there's 3 axes of reflectional symmetry. Each axis goes through one of the vertices in the midpoint of the opposite side. So the right one there, yes. So this is the right axis for this one here. You can reflect the whole plane in this axis indicated by my pen there, and it leaves the triangle as the same triangle. So it's symmetry of the triangle. Of course, it moves the vertex labels around. The A stays fixed because that's the reflection axis is going through A. The other 2 swap. And so there's 3 axes like that going through each of the three vertices. Now he's also recorded them or used notation for them, which we did see briefly in first year, which is an example of these permutation notation. So this is the kind of notation that it's not denoting, it corresponds here to transformations of the plane. But strictly speaking, this is just a notation for functions from a set of 3 labels to itself. So the identity says send A to A. So the top is the input, the bottom is the output. Then B to B, send C to C. This rotation sends the vertex A to vertex B to C, and C sends A. So we got one of those permutation symbols representing each of these symmetries of the triangle. Now, we'll be meeting and talking about these kinds of things in lots of detail in the course. Okay, so that's just our first view of them, and you have had a bit of exposure in the first year. There's a whole separate chapter on permutation groups, so we'll be working through that. Now he's also gone to the trouble of naming them. So you got id is the identity, row 1 and row 2, so it's a Greek letter row, equivalent to the R. So row 1 and row 2 are the other 2 rotations. Sometimes people consider the identity element a rotation. It's a rotation by the 0 angle. Certainly not any kind of reflection, but you can consider the identity element as a kind of trivial rotation. And then the 3 reflections are mu1, mu2, and mu3. Now, if you look over the page, or further down the web page, he's gone to the trouble of working out the full decay table. So this is 6 elements. There's 36 different elements in the body of the table there. Okay, there's a lot of detail concern there, and to construct this from scratch would be a lot of work. Except one of the common behaviors or common patterns that we start to see here, and this is an example of a true fact. I've done this out on my book here, so I'll just show you how I've adapted this diagram. What have I done here? I've destroyed my diagram by drawing lines over it. You can classify, so remember, there's the identity, the 2 rotations, and the 3 reflections. So these 3 I'm calling rotations. So the identity is rotation by 0 angle. One of them is a third of a turn, the other one is 2/3 of a turn. It's traditional to use the letter S to refer to reflections. Maybe it comes from the German word for reflection. Or maybe it's just because it's the letter after right. So S refers to the reflections. When you look at what's going on in the body of the table, you always see that if you compose one of the rotations with one of the other rotations, you get another rotation. So just by the pattern, a rotation composed with a rotation gives you a rotation. Similarly, if you compose a reflection with a reflection, you always get a rotation. The other types of product, when you compose a rotation with a reflection, you get a reflection. And when you compose a reflection with a rotation, first doing the rotation, then the reflection, you always get a reflection. Those things are true in general. So those are, again, just like associativity of composition of functions, that's true in general. So is that idea of composing rotations and reflections. So in general, composing rotations about a fixed center point. So the center point we're talking about in the rectangle or the triangle case is just the center of the object. Okay, these are triangles are regular isosceles triangles, so they have a center. So in general, composing rotations about a fixed center point, let me just be a little bit precise, and reflections in axes through that center point. So if you think about it, when you look at the triangle, all those three axes of reflectional symmetry, they all go through the center point of the rectangle. So in general, in R2, in the plane, such compositions always follow this behavior. When you compose a rotation with the rotation, you get a rotation. So rotation after rotation always gives you rotation. Reflection after another kind of reflection always gives a rotation. And the other types give reflections. So just be clear, R and S are not specific elements here. It's just when you take, I'm just trying to describe, you take some rotation, another rotation, those always get rotation. Now the explanation for that can be given fairly easily. It's easy to see that when you compose two of these rotations by certain angles around the same point, all you're doing is rotating the plane through the sum of the two angles. So you're still rotating. The other ones are slightly, maybe you'd have to think about it a little bit. A fundamental thing is that with objects in the plane, you have this concept of handedness. If you think about the pattern of the outline of a hand, there's two types of hand you can draw. Two types of awful picture of a hand you can draw. You can either draw a left-handed one or a right-handed one. Now, if you're looking at, that's insane. I should be drawing a clear thumb. That's the thumb there. But there's a left-handed hand and a right-handed hand. The technical name, if you want to sound fancy talking about this thing, it's chirality. C-H-I-R-A-L. Chirality. That's the notion of handedness. When you apply a rotation to something, you aren't changing the handedness. If you take a left hand and rotate it, it always remains a left hand. However, when you take a left hand and reflect it, just reflect its outline, suddenly the thumb's over here. So suddenly it's looking like a right. I can never make my left hand without turning it around, without reflecting it. I can never make it match that pattern. Because if I do move the thumbs over there, suddenly the fingers are pointing down. There's two versions of that. So if you take your left hand and you apply one reflection, and then reflect it somewhere else, it's going to be back to being the left hand. And so as a single transformation, if you move a left hand to another left hand, it has to have been a rotation. Because any reflection will always flip the left hand into a right. So that's why S after S is always an R. Similarly, if you do an S after R, it always gives you an S, because if you first, remember this is on the right, so if you take your left hand, first rotate it a little bit, so it's still a left hand. Then you perform the reflection, it's changed to a right hand. So the overall transformation must have been a reflection in order to change the left-handed thing into a right-handed thing. And similarly, when you consider it. So what we're seeing there, that pattern, what we're seeing with the symmetries of a triangle is true in general. about transformations like this, always about a fixed center point, or reflection in an axis through that center point. That's true in general. And that's our second example of a group. For the very same reasons as before, looking at the rectangle, this system does satisfy all four of the group axioms. Okay. The elements are no longer, well, all of the, you see you've got I identities along this diagonal here, all of the reflections are self-inverse. mu1 after mu1 is the identity, mu2 after mu2 is the identity. When you perform the same reflection twice, everything goes back to this way. The identity is self-inverse, but the other two rotations are not self-inverse, but they're inverses of each other. So P1 after P2 is the identity, P2 after P1. P1 is rotation by a third, P2 is rotation by 2/3, so then you compose them, you're rotating by one full rotation, so that's the same as the other. So that's the second, or that's another example of a group for. Okay. Okay, so that brings us to the end of today. So really, we just met the definition and some starting important examples. What we'll do on Thursday then, okay, we aren't ready quite to dive into the exercises, but we'll start to work through that second section on the reading notes. You see there the basic properties. So that's the next section in chapter 3 there, where we start to build up the abstract groups here. We start to look at the definition and what consequences we can draw from the definitions. Okay. Okay, so I'll see you on Friday morning, and then we'll have another lab session on Friday evening. And please do. Okay, I forgot to record the actual visual screen of what I was doing there, but